Hey, it's Dr. Doobie again, and I've got a tutorial for you on multi-stage stripping column. You can see it's nighttime here in Tuscaloosa, Alabama. I'm getting ready for bed. I'm tired. Anyway, this is an ammonia stripping column, and we will solve this using the Lewis method. Here is the problem statement. 100 moles per second of a water stream with 5% ammonia is fed to a 5-stage stripper operating at 60 degrees C and 1 atmosphere. Enough pure air is fed to strip out 90% of the ammonia from the water. Determine the flow rate and composition of all streams. As usual, make some assumptions. Only the ammonia distributes between phases, so water does not go into the air does not dissolve into the water. Vapor-liquid equilibrium is achieved, and the system is isothermal and isobaric. We will not assume that the gas and liquid flow rates are essentially constant because this is a relatively large concentration of ammonia. The first thing we'll do is draw a labeled process flow diagram. I'll just draw the stage 1, and our calculations will continue on down the column stage by stage. This is the stage, and it has a liquid feed going into it and a gas coming out containing the stripped out ammonia. This stream here is coming from stage 2, and this is the liquid stream leaving stage 1 going to stage 2. We'll label these streams L0 and X0. That's coming from, you might call it a fictitious stage above stage 1. That's our feed. Leaving stage 1, we have the liquid flow rate L1 and its composition X1. Leaving stage 1 in the gas phase, we have G1 and its composition Y1. And coming into stage 1 from stage 2, we have G2 and its composition Y2. The temperature and pressure were both specified for this system. And I will not put the numbers in here just to keep things nice and simple and clean. The idea here is that if we can figure out what these flow rates and compositions are, then we should be able to use mole balances and equilibrium relationships to figure out these. Then these become the top streams above stage 2, and we can calculate the streams at below stage 2 and continue on down the column stage by stage. Now we will conduct a degree of freedom analysis. The feed, liquid flow rate, and composition are specified, as are the temperature and pressure. But we do not have specified the gas flow rate and composition leaving stage 1 or coming into stage 1, or the liquid flow rate leaving stage 1 and its composition. So we'll have 6 unknowns. Let's write those down. So the unknowns, and there's 6 of them, are L1, X1, G1, Y1, and G2, Y2. The equations that we can use to relate these, and hopefully there will be 6, are, let's see, we have 3 components. So we have 3 mole balances. And they are, well, we could use air, water, and ammonia, or a total mole balance and either of the two. So what we're going to do here is use the water mole balance. We're going to use the ammonia balance, and we'll use a total mole balance. You'll see that in the spreadsheet solution. What else do we have? We have one equilibrium equation. That's for the ammonia. And we have a process specification. That's the 90%. That's 5. We need another one. Well, you might guess from our previous discussions that we need one guess. And that will be the water flow rate. So guess the water fed. And I'll show you how we do that in a minute. So we'll guess that. Now we have 6 relationships, equations, and 6 unknowns. So we should be able to solve this problem. Now we get to the fun stuff, which is writing the equations and solving. So let's look at the water mole balance. The water coming in with the feed is L0 times 1 minus X0. And that has to equal the water leaving stage 1, which is L1 times 1 minus X1. For the ammonia mole balance, we have the ammonia coming in with the liquid feed is L0 X0 plus that coming in with the gas from stage 2 is G2 Y2, and that's equal to the liquid leaving, the ammonia in the liquid leaving stage 1, which is L1 X1, and the gas leaving stage 1, G1 Y1. The total mole balance we just look at the stream feed rates. Coming into the process, into stage 1, we have L0 and G2. And that has to equal the streams leaving stage 1, G1 and L1. Let's see, we have the ammonia equilibrium. That will be the partial pressure of ammonia, which is Y1 times the total pressure. That has to be equal to some function of the liquid composition leaving stage 1. But we'll write here the partial pressure of ammonia. We'll have an expression for this partial pressure in terms of the liquid composition here. So Y1 times total pressure will be equal to some function of X1. We'll get to that in a minute. Now we also have the process specification, which is the 90%. and that is that the gas flow rate here contains 90% of the ammonia coming in from the liquid feed. So we'll say that G1, Y1 is equal to 90% or 0.9 of the ammonia in the liquid feed, which is L0, X0. We also have our guess. And that will be the water being fed to the system, which is G1 times 1 minus Y1. And, well, we haven't made a guess yet. Let's say 50 moles per second. Seems like a reasonable number. Now, we have 6 equations, 6 unknowns. We can solve this. Here is the data for ammonia vapor-liquid equilibrium that you find in Perry's handbook. The composition in the liquid phase is given as a weight ratio, grams of ammonia per 100 grams of H2O. So for instance, a 50% by weight solution is given by the number 100. 100 grams of ammonia per 100 grams of water. And data for various ratios like that. The mole fraction liquid phase is not given. I'll get back to that. And here is the partial pressure of the ammonia in millimeters of mercury for different temperatures. It starts off at 50% by weight for 0 degrees C, but it doesn't start off until 20% by weight for 60 degrees C, because the vapor pressure is so much higher at the higher temperature. Now, what we really want is mole fraction in the liquid phase, and so here I've converted the weight ratio to a mole fraction. That's a calculation that's fairly simple, and you should be able to do that from skills you learned in your material and energy balance class. Why don't you give a couple of those a try? Make sure you get the same number as I do. Here I've plotted that data as partial pressure of ammonia versus the mole fraction in the liquid phase. And as you'd expect, for a certain mole fraction, you get a higher partial pressure at the higher temperatures. And here is the data that we will use in a stripper example, which will be 60 degrees C. Now, each of these curves I have fit with a polynomial equation. And so this curve here for 0 degrees C has this equation. This is for 10, 20, and 60 degrees C. So this equation then says that the partial pressure of ammonia is equal to this function of the liquid phase mole fraction with an R-squared value of 4/9, so it's pretty good. Here is my spreadsheet solution, and I'd like to take you through the calculations. You can follow along with the accompanying Excel spreadsheet, Ammonia Stripper. In green, we have the specified values. So we have the pressure, 1 atmosphere, the temperature, the percent removed, the liquid flow rate, that's our feed, and its composition, 5%. And also, we specify that the gas phase, the air that will strip out the ammonia, has no ammonia in it to start with. I start by guessing values for the liquid phase composition leaving each stage here. And I just made that go in an even amount from stage to stage. And we also specify here the gas flow rate, which will be one of the things that we change to solve the problem. We have three material balance equations embedded in this spreadsheet. The first one is for the liquid flow rate. This is a water balance, water mole balance. We say that the water coming into stage 1, which is just 100 times 1 minus x, has to be equal to the water leaving stage 1. And that would be this number times 1 minus this mole fraction. So then this cell just contains L1 is equal to L0 times 1 minus x0 over 1 minus x1. And then that is copied all the way down from stage to stage. And since these numbers were guessed, this is a direct calculation. The gas flow rate is calculated based on an overall balance around each stage. So the amount of material going into the stage is the gas from the feed and the liquid from stage 4. That has to equal the amount of liquid leaving the stage and the amount of gas leaving the stage. And so this number here is just the gas feed plus the liquid from stage 4 minus the liquid from stage 5. The gas phase composition is determined from a mole balance of ammonia around each stage. So for instance, the ammonia coming into stage 5 is from the gas feed and from the liquid coming from stage 4. And then the ammonia that leaves is the liquid leaving stage 5 and the gas leaving stage 5. So this number here is just calculated based on this plus this minus this and the whole thing over the gas flow rate. So now the iteration occurs where we look at this chosen value for the liquid phase composition and calculate using that the partial pressure of ammonia. Now that should equal the mole fraction of ammonia we get in the gas phase from a ammonia mole balance times the total pressure. And if they're not equal, then a solver will then adjust this value until the equation here, which is Y of ammonia times the total pressure minus the pressure that we get for the ammonia using that polynomial equation. And we make that cell equal 0 by adjusting x. So this y here is this value. The pressure here is this value. And the ammonia partial pressure here is this value. So this is changed by changing the mole fraction of the liquid phase until this is equal to 0. And then that calculation continues down the column. Here I've done just that. I've used Solver to change the liquid phase mole fractions so that the ammonia equilibrium equations are all satisfied. Now that is the first pass with the gas flow rate still at 50 moles per second. That's obviously not a very good choice because the stage-by-stage calculation shows a liquid phase composition of 0.0009 mole fraction, whereas the overall material balance would give you a 0.0053 mole fraction. The difference here is the two values subtracted from each other times 1,000 to make it more sensitive. So Solver is going to have to change this gas flow rate and then go through the entire calculation again, and this process will be repeated until this is satisfied. Here I've pressed Solver, and now you see that all the ammonia equilibrium equations are satisfied, and we have reached the stage-by-stage calculation that matches the overall material balance. And so this is the final answer. So it requires 27.8 moles per second of gas to accomplish this 90% removal. You can compare this number to 63.3 moles per second for a two-stage separator and 236.5 moles per second required for a one-stage. So you really can see the benefit of adding more stages to a separation.